Airplane manufacturers often prefer using rivets over welding for several reasons. 1. Material integrity. Different materials used in aircraft construction, like aluminum and titanium, respond differently to heat. Welding can cause changes in material properties, such as weakened areas or stress concentrations, while riveting preserves the integrity of the materials. 2. Weight considerations. Riveting allows for the construction of lightweight structures. Welding can often add unnecessary weight due to the need for additional reinforcement or fillers. 3. Flexibility and repairability. Rivets offer better flexibility and can allow for some movement between parts, which is essential due to the dynamic forces experienced in flight. Additionally, if a part needs to be repaired or replaced, removing rivets can be simpler than reworking welded joints. 4. Thermal effects. Welding generates a lot of heat, which can lead to warping or distortion in the materials involved. Riveting avoids these thermal issues, maintaining the original shapes and dimensions of the components. 5. Manufacturing techniques. The assembly process for aircraft involves joining many different parts, and riveting enables efficient assembly with automated machines. This process can be faster and more consistent than welding. 6. Safety and inspection. Riveted joints can be easier to inspect for quality and safety. Many rivets can be checked visually, and non-destructive testing methods can easily be applied to inspect the integrity of riveted joints. 7. Aviation engineering has a long history of using rivets, and substantial research and testing have established best practices for their use in aircraft design. Overall, while welding has its applications in aviation, rivets provide a combination of benefits that make them the preferred choice for many structural applications in aircraft manufacturing. Riveting and welding are two distinct joining techniques used to assemble parts. The primary differences are: 1. Riveting involves using a rivet, which is a small metal pin with a head on one end, to join two or more parts together. Welding, on the other hand, involves melting the base materials to form a strong bond. 2. Joint strength. Riveted joints can be designed to be strong and durable, but they may not be as strong as welded joints, which can provide a continuous unbroken bond. 3. Material distortion. Riveting can cause less material distortion compared to welding, which can introduce heat-induced stresses and distortion. Riveting is widely used in aircraft manufacturing due to its reliability, inspectability, and ability to join thin materials. Some benefits of riveting in aircraft manufacturing include these qualities. Firstly, structural integrity. Here, rivets are used to assemble aircraft structures, such as fuselage and wing sections, to ensure strength and durability. Secondly, fatigue resistance. Riveted joints can be designed to resist fatigue, which is critical in aircraft structures that are subject to repeated stress and vibration. Thirdly, inspectability. Riveted joints are relatively easy to inspect, which is essential for ensuring the safety and airworthiness of aircraft. Now let's talk a bit about some other applications of riveting. Riveting finds its way into loads of different industries and uses, far beyond what you might expect. Aerospace and aeronautics, riveting is absolutely essential in the manufacture of aircraft, spacecraft, and even missiles. Riveting is used in the production of vehicles, especially for assembling body panels and other structural components. 2. Riveting is used in building construction, particularly for assembling steel frames and other structural elements. 3. Riveting was historically used in shipbuilding, although, to be fair, welding has largely replaced it in modern shipbuilding practices. 4. Riveting is used in the manufacture of industrial equipment, like machinery and storage tanks. New technologies are emerging to replace riveting in aircraft manufacturing, focusing on improving structural integrity, reducing production costs, and increasing efficiency. Some of these technologies include welding techniques. 1. Laser beam. Welding, LBW, offers superior accuracy, weld quality, and minimal distortion, making it ideal for welding and drilling jet engine components. 2. Electron beam welding, EBW, provides a concentrated heat source, resulting in minimal distortion and high-quality welds, particularly suitable for titanium alloys. 3. Friction stir welding, FSW, a solid-state process that creates strong joints through mechanical deformation, suitable for welding aluminum alloys. 4. Variable polarity plasma arc welding, VPPA, developed for welding thicker aluminum alloys, offering cathodic cleaning and penetration benefits. Advanced joining methods, diffusion welding, DFW, creates joints through pressure and heat without macroscopic deformation, valuable for combining superplastic forming, SPF, with titanium alloys. Friction welding, FRW, joins metals through mechanical deformation, effective for circular cross-sections and high-temperature applications. Other technologies such as laser riveting, which uses powerful lasers for precise joining, potentially replacing traditional riveting methods. There is also the automated riveting systems improves efficiency, accuracy, and productivity in aircraft manufacturing processes. These technologies offer several benefits, which includes improved structural integrity, where welding and advanced joining methods can create stronger, more durable joints while also reducing production costs. Automated and efficient processes in welding minimize labor hours and costs. Advanced technologies streamline production, enabling faster and more reliable assembly. Enhanced sustainability is also achieved by some technologies, like laser welding, which produces less waste and consume less energy. As the aviation industry continues to evolve, these technologies are likely to play a significant role in shaping the future of aircraft manufacturing. There are several ongoing research projects and advancements in welding technologies for the aviation and aircraft manufacturing industry. Some of the notable ones include thermoplastic composites. Welding. Researchers are exploring the use of thermoplastic composites, TPCs, and welding technologies to create lighter and more efficient aircraft structures. Techniques like ultrasonic, induction, and resistance welding are being developed and refined for this purpose. Friction stir welding, FSW. This is a solid-state welding process that's gaining traction in the aerospace industry. It's being used to join aluminum alloys and other materials, offering advantages like low distortion, high strength, and reduced residual stresses. Laser welding and additive manufacturing. Laser welding and additive manufacturing are being used to produce complex geometries and structures with high precision and accuracy. These technologies have applications in repair and overhaul, as well as in the production of new components. Advanced friction stir welding techniques. Researchers are developing new friction stir welding techniques, such as bobbin tool friction stir welding and friction stir welding with adaptive control, to improve process efficiency and quality. Real-time monitoring. There's ongoing research into real-time monitoring systems for welding processes, which can enhance process control, quality assurance, and operational safety. Some notable organizations involved in these research areas include Daher, a company that is developing advanced welding technologies, including induction welding for thermoplastic composites. Kawasaki Heavy Industries. This company is into researching innovative, integrated out-of-autoclave TPC processes, including local co-consolidation and welding. Collins Aerospace is also working on thermoplastic composite materials and welding technologies. Organizations such as Airbus is exploring the use of friction stir welding and other advanced welding technologies for aircraft manufacturing. NASA also utilizes friction stir welding in the production of rocket components, such as the Space Launch System's liquid hydrogen tank,